Hi everyone! We are glad to present you our work on a new algorithmic improvement for ptychography. I'm Jonathan Dong, and with Lorenzo Valzania, we will show how to initialize efficiently a ptychographic reconstruction using a technique called spectral methods. This work was performed in the Laboratoire Kastler-Brossel in Paris under the supervision of Sylvain Gigant, and the experiment was realized at EMPA in Switzerland. Ptychography is a computational imaging framework which has been introduced back in 1969. The experimental setting is the following. An illumination probe is scanned onto an object to study, and the resulting diffracted patterns are recorded on a camera. From this stack of camera images, one then reconstructs the amplitude and phase of the object using a complex reconstruction algorithm. This is in sharp contrast with the simplicity of the experimental setting, which explains why ptychography has been successfully applied in many different settings, from X-ray and terahertz imaging to electron microscopy. It has also inspired a variant in the Fourier domain called Fourier ptychographic microscopy. Let's settle down the equations of this computational problem. We are looking for a planar object denoted by psi. A probe, denoted A, is scanned onto this object at multiple positions XL. Then this electric field is propagated to the camera detector, which measures its intensity. This explains why there is this element-wise modulus square operation. This experiment is repeated for multiple probe positions, denoted by L, and from this stack of images Y, one wants to recover the object psi. This inverse problem is a phase retrieval problem because of the phase information that is missing due to the modulus operation. The complexity of the reconstruction comes from this missing information. The problem becomes non-convex, and many different strategies have been proposed to reconstruct the object. In ptychography, we can solve this phase retrieval problem thanks to the overlapping probe positions, as we have multiple images carrying information for each unknown parameter to find. As with all non-convex optimization problems, we will iteratively find a good estimate. For our starting point, we can choose a flat or random initial guess, or we can quickly build a heuristic estimate from a subset of images. This initial guess is then refined using an iterative algorithm. There is a large variety of possible algorithms here, from the ptychographic iterative engine, abbreviated PIE, to convex relaxations, including gradient descent optimization or alternating projections. Here, we will use gradient descent and PIE, as they are two computationally efficient techniques commonly used in practice. The spectral method we will introduce can be regarded as a new initialization strategy. As such, it replaces the previous heuristics and can be followed by any iterative algorithm. Compared to the previous initialization strategies, we use the full dataset and do not suffer from resolution loss due to the use of a subset of the collected data. This method is fast and deterministically converges towards an estimate that will hopefully be close to the object to recover. Thanks to this good initial guess, this will help any subsequent iterative algorithm. In the following, I will first introduce these spectral methods, how to define them and what is the intuition behind them. Then, Lorenzo will show how they are useful in practice and what can be done next. To introduce how to design spectral methods, it's useful to start from the forward model of ptychography. The object is illuminated by a shifted probe illumination, and ptychograms are recorded after light propagation. This can be put in the following vectorized formalism. The object, represented as a vector, is multiplied element-wise by the probe several times, one for each probe position. Then the resulting field is propagated, which is modeled by a linear operator. Finally, an element-wise modulus square operation corresponds to the intensity measurement on the camera. This can be rewritten as y is equal to the modulus square of a certain matrix S times our object psi. Each intensity measurement comes from the product of a row of S and the vector psi. Thus, each yi is equal to the modulus square of the scalar product, and this scalar product is computed between a known vector Si and our unknown object psi. If we look closer at what this equation means, there are two possible cases. When Si and psi are correlated, they point in the same direction and the measured intensity yi is high. On the other hand, when Si and psi are uncorrelated, the measured intensity yi is low. We would thus like to exploit this information with a simple algorithm, and this will correspond to our spectral methods. The idea is that if we have sufficiently many measurements, this heuristic will return an estimate close to psi. Hence, we would like to build a matrix giving more weight to Si when it is correlated with our unknown psi. We do it with the following matrix Z. Each term in Z is a rank 1 matrix pointing in the direction of Si that will weight according to the measured intensity yi. We sum over all the measured intensities and hope that the leading eigenvector of this matrix will be correlated with psi. This idea was proposed as part of the Wirtinger flow algorithm, where the spectral initialization was followed by gradient descent. The heuristic of spectral methods is still valid when we introduce an increasing function of the measured intensity. Large values of y will still be weighted more than small intensities. With this preprocessing function tau, we obtain a more general setting that will be useful later. Several preprocessing functions have been proposed. Two simple ones are the identity function, which we have introduced already, and the threshold function, which interestingly has previously been discussed for ptychography, based on a completely different theoretical basis. Here, we would like to point out a particular preprocessing function that we will use, 1 minus 1 over y, which was proven to be optimal in some theoretical setting. Why is this algorithm interesting to use in practice? First, we compute the leading eigenvector of z using power iterations, which means that we repeatedly multiply by z, and this process is guaranteed to converge. This is very different from other optimization frameworks, where finding a global minimum is a non-trivial task. Since we complement the spectral method with an iterative optimization, the whole algorithmic pipeline that we will use is still not guaranteed to converge, but the first step is, and we'll see that this increases the robustness of the overall algorithm. Second, it is possible to efficiently multiply by z. Thanks to its structure, we first compute the forward model of ptychography when we multiply by the matrix S, then compute an element-wise multiplication, and then perform a backward pass. This last step is related to backpropagation in deep learning, which we can see with the transpose operator. This is equivalent to any gradient descent iteration or PIE, which are commonly used already. Third, similar to gradient descent and PIE, we can also parallelize this computation image by image. This keeps the memory cost of the resulting technique reasonably low. For all these reasons, spectral methods have gathered a lot of attention from theoreticians studying the phase retrieval problem. They usually tackled the generic case where the matrix S is completely IID random. This is not the case in ptychography. Here, we see that S presents this block structure with a probe elimination and with propagation. Next, Lorenzo is going to show how to translate these findings to the practical case of ptychography.
Now I'm going to walk you through all the steps one by one. In practice, first we need to construct a ptychographic setup characterized by a certain probe function and a known propagation kernel bringing from the object plane to the camera plane. And these two pieces of information allow us to construct the sensing matrix S. Second, we collect the ptychograms, preprocess them, and store the results along the main diagonal of this diagonal matrix. Third, we construct the weighted covariance matrix Z. and then we are ready to apply the spectral method, consisting of retrieving the leading eigenvector of Z. Finally, the spectral estimate may be further refined with any iterative optimization algorithm, be it gradient descent or more dedicated ptychographic routines like the ptychographic iterative engine or PIE. We demonstrated our method with an imaging setup working with terahertz radiation, equipped with a CW gas laser whose emission line can be tuned between the mid and far infrared range. We also used an uncooled microbolometer array, which, although designed to work in the mid-infrared range, allowed us to perform ptychography in the far infrared range too. We used a near-field ptychographic setup where free space propagation was modeled with the angular spectrum method. The object was a transparent plate where 3 intersecting rings were ablated at different depths. It acted as a phase-only object, and it was scanned by a probe defined by a circular aperture. Now you can see that even with a probe like this one displaying a low degree of randomness and structure, the power method yielded a spectral estimate already well correlated with the ground truth. At that point, only few gradient descent iterations, with the step size set by a backtracking line search, were needed to obtain a satisfactory reconstruction, both in terms of lateral and phase resolution. For comparison, a standard Vertinger flow gradient descent algorithm without a spectral initialization converged 3 times more slowly and at a final error higher than the one reached with the spectral initialization. We can improve the reconstructions without the spectral initializations with a more careful choice of the step size, however yielding, even in this case, as you can see from the green trace, a rose result within a comparable number of iterations. More interestingly, we found out that the spectral initialization proves crucial to reconstruct datasets at low signal-to-noise ratio, where extracting useful information out of the noise level turns out to be more challenging. In particular, we observed a reduction of the error by a factor of 2 at the lowest signal-to-noise ratio. Now, although spectral methods were conceived to complement gradient descent algorithms, a spectral estimate may be used as an initial guess for any iterative ptychographic algorithm. And here we show the same comparison with reconstructions obtained from a PIE algorithm with and without a spectral initialization. Even in this case, spectral initializations managed to drive reconstructions beyond local minima, especially with higher amounts of noise. We should keep in mind that the power method only updates the object transmission function using our estimate of the sensor matrix S, which is kept fixed. Therefore, in the experiments that we have just discussed, before starting the spectral method, we calibrated the matrix S with an algorithm capable of optimizing simultaneously for both the object and the probe. However, we would like to stress the fact that our spectral method is fully compatible with large-scale ptychographic procedures that need to optimize for both the acquisition parameters and the object transmission function. For example, one can think of performing a few power iterations to update the object, then interchanging the role of the probe and the object to update the probe while keeping the object unchanged, so on and so forth. There is further room for improving spectral methods, and what is interesting is that the same tools improving iterative optimization algorithms, like gradient descent for example, can be implemented on spectral methods as well. Specifically, stochastic power iterations as well as linear algebra approaches can further accelerate the retrieval of the leading eigenvector. But the most efficient way to deliver more informative spectral estimates is to multiplex complementary information in the tychograms by carefully optimizing the sensing matrix, which is what we are going to discuss more in detail now. In order to optimize the sensing matrix, we aim to bring the measurement setting closer to those random IAD settings for which spectral methods were originally developed. And this regime can be reached in a tychographic setup as well, even though only one probe function is used throughout the whole acquisition. And this is possible because using a speckled probe function with a grain size much smaller than the shifts in the tychographic scan, we are almost sensing the object with a set of statistically independent probes. Up to now, we have only tuned the spatial distribution of the probe, but we can also act on the diffraction regime in our measurements, characterized by the Fresnel number. In particular, we can predict that the lower the Fresnel number, the stronger is the mixing of the information contained in our phase retrieval problem, making it easier to solve. Our expectations are indeed met by our simulated results. Finally, we were also able to confirm that the optimal preprocessing function that was theoretically derived for another setting, even in this setting, delivers better results than using the bare tychograms with no preprocessing. To wrap up, we have provided the first experimental demonstration that spectral methods, originally designed for random settings, can benefit tychographic phase retrievals too. We reported 3 times faster and better tychographic reconstructions with a spectral initialization than with a standard gradient descent algorithm. Notably, the crucial impact at low signal-to-noise ratio was also observed. We listed a few procedures to make spectral methods more efficient, and among them, the optimization of the sensing matrix was discussed in detail. Throughout the whole presentation, we have highlighted the compatibility of spectral methods with other iterative tychographic solvers, and most importantly, the fact that they come with no additional computational complexity than a gradient descent algorithm. With this, we would like to thank our collaborators in Switzerland who played a major role at the early stage of this project, the Swiss National Science Foundation and the European Research Council for their financial support, and of course you for your kind attention. And don't hesitate to get in touch with us by email or through the Slack workspace. Jonathan and I will make sure to answer all your questions. So see you there.